In this series, we're trying to build a vacuum tube replica of the MC14500. Now, I say replica, but through the rest of this video, we're going to discover that we might be deviating a little bit away from that. And that's because I have another series where I take that Motorola MC14500, the actual silicon chip version, and I build it up on a breadboard as essentially a 1-bit breadboard computer. And it was awesome. It was tons of fun to build that up on the breadboard. And in the previous episode of that series, we actually got it working. We ran some pretty cool code on it. And that code was an increment program. And what that increment program did was it took whatever 5-bit number was on the input and whatever 5-bit number was in the scratch register and added them together and then gave us the output. Only it did it 1 bit at a time. But because the Motorola MC14500 is a quirky, weird little chip, addition was really difficult on it. It took us a huge number of steps just to add two 1-bit numbers together. So I've been losing sleep about this because I want the tube version to be a little better than that. I want the tube version to be able to do addition and subtraction with ease. And so I started thinking about what I can do about this whole logic unit situation in the MC14500 because we're building something from scratch, which means that we're not necessarily limited to doing exactly what they did. Maybe we can make some changes. So what I want to do today is I want to take a look at maybe some changes that we're going to make in the future, some huge design revisions that are going to make this processor a little less Motorola and a little more Usagi Electric. So let's hop over to the bench, take a look at the huge design revisions that we're going to do, and then we'll pull the actual computer out at the end, and I've got some extra boards that I cut up for it. And so we'll slot those boards in place and give it a quick test. So let's hop over there and get started. So what we have here is the block diagram for the MC14500, and I actually really like the layout of this chip. But because the original designers designed this with just a logic unit, the only way to do binary addition is to essentially brute force your way through it, doing the individual logic steps required. And that meant that in order to do 1-bit binary addition with carry took about 12 steps. But if we compare that to something like the SAP1, it can do binary addition on 8 bits in just like 3 steps. Whereas if I wanted to do 8 bits of binary addition with just the MC14500, it would take over 100 steps, I think. So that got me thinking. I'm essentially building up the tube version using this block diagram as a blueprint. But because there's a lot more involved than just the block diagram, I came up with this gate level replication of that block diagram. And this is what I've been following along building. And you can see that over here on the left, we've got our 4D flip-flops. Then we have our large decoder with 16 NOR gates here. And that's pretty much what we've built so far. And so we're just slowly working our way from left to right across this. And it's a little difficult to see on here, but the logic unit is essentially just this small bit right here. And you can see it's actually an incredibly simple logic unit. And essentially this is kind of like a diode decoder that goes into a multiplexer. Incredibly simple, very low tube count. This was great. However, it should be noted that this is not how the logic unit was built on the actual chip. A while back, I asked Curious Mark and Ken Schrift to help me reverse engineer the chip because I was curious how they were doing things on the inside. And Ken wrote a phenomenal article on his website. So I'll put a link in the description below, but definitely go check that out because he goes into a lot of fantastic detail about how the chip was constructed, how CMOS logic works, and he goes into detail about how the logic unit itself works. Now this was the closest way I could replicate the way it actually worked using just a Logisim. That's the program that I do all of my logic testing in. But it's incredibly convoluted and difficult to understand. So I simplified it one step further. Now this is a lot easier to understand. This row of AND gates is really just a collection of essentially selectors to allow whatever logic is happening on the other side of them to pass through to the data input of our result register. So for example, we have the result register coming into one input of our XNOR gate here, and we have the data coming into the other input of the XNOR gate. So this gate is always performing the exclusive NOR of the result register and the data. And we only let the output of that gate pass through when we turn the XNOR control line on. And then that allows this data value to pass through. And so this was the simplest way to represent the existing logic unit. But even still, I feel like we could simplify this even further to help us visualize what modifications we want to make to essentially get to where we want to be in terms of functionality. So all of these different gates and selectors and the big OR gate on the end, let's just put all of that into essentially a black box. And so essentially we just have a big black box in the middle, and we don't really care how it does what it does. We just care really what the inputs are and what the control lines into it are. So essentially we just have two inputs. We have the data coming in and we have the results register coming in. And then we have 7 control lines. We have load data complement, logical and complement, logical or complement, and exclusive NOR. And depending on which one of these are selected, it's going to perform that operation on the two inputs and then give us the output through here, which can then be stored in our results register. As long as we keep 7 control lines coming in, 2 inputs and 1 output, well, this black box can essentially just do whatever it is that we want it to do. And so I had to think about it. I really want it to do addition and subtraction as well as a few logic operations. So this was what I came up with. Instead of just a logic unit, now we have an arithmetic logic unit. And we still have 2 inputs and 7 control lines coming in. So we could just plonk this down right where the old logic unit was, and everything should work all right, except that our instructions now do something a little different. So the first instruction is going to stay the same. We want to load the data into the result register, and so that one doesn't change. But the 6 after that change pretty dramatically. So I wanted to do addition and subtraction, so I put those in right off the bat because they were the most important. Now in the previous logic unit, it was very important to have the OR with the complement because that meant we could force a 1 into the result register regardless of what was already stored in there. We used this all the time when we were running our programs. So I just decided to have an instruction that forces a 1 into the result register regardless of what's going on. So those are our 3 brand new functions. And then after a bit of Googling, it seems that most ALUs also have and, or, and exclusive or. And I can see why they do this because you can do and then output the inverse of that, and that's essentially NAND. Or you can do that with OR and output the inverse of OR, and that's a NOR. And the same with exclusive OR and exclusive NOR. That puts a ton of functionality into our arithmetic logic unit while still retaining just 7 control lines. So we're not going to affect the rest of the design in any way. So we have a block diagram blueprint. It was time to start figuring out the logic behind this. And this was the first iteration that I came up with. And it looks pretty wild because there's a lot of stuff going in a lot of different directions, but there's just a few main components. Right up here we have a full adder. So this is a binary addition unit with carry in. And then coming out of that we have the sum, which comes all the way down here and ultimately makes its way over to the result register. And we also have the carry out, which makes its way over to the carry here. And then when we do subtraction, we want to have an exclusive OR gate set up on one of the inputs into the full adder. And then down here on the bottom, we've got our and, or, and exclusive OR operations. And, all of these are gated through some and gates here, so that way only the one that we're selecting is making its way to the result register. And so using this as a blueprint, it was time to go one step more complicated. And it looks a little insane. There's a whole lot going on here, but if you break it down, you can start to see the individual pieces. This is the carry register here, these 8 NOR gates, and then this is the result register here, these 8 NOR gates. And actually the result register hasn't changed from our original design. All I did was copy it up to the carry register. Now to the bottom left of our carry register is our full adder here. We have our exclusive OR gate up front here. And then in the bottom left down here, we've essentially got a miniaturized version of the old logic unit that we had. And so the next step was to take this massive collection of gates and stuff it into the total gate representation for the entire chip. So aside from the logic unit, nothing else has changed. But the logic unit has gone from a simple 5 gates to close to 50 gates now. So I've made life exponentially more difficult for me, but this should bring the capability of the processor up dramatically. Now this all simulates really well in Logisim. I've been doing a lot of testing on it, and I can do full binary addition or subtraction in just 2 steps. So I went from 12 down to 2 steps, all contained within the original architecture. This, in my opinion, is the ultimate evolution of the Motorola 1-bit design. But because this is now a dramatically different design at the heart of it, it's hard to call it a replica of the MC14500. So I've been trying to think of a different name that I can start calling this processor. And since it's something that we're building here on the Usagi Electric channel, I was thinking, why not call it the UE14500? It's the Usagi Electric microprocessor. Now, before we dive into building this, there's actually one more step that we gotta do before we get this far. And it's not shown on this diagram, but it's the problem of buffering outputs. All 16 of these lines spear off and go into different directions all throughout the processor here. So it would be best if these would not get loaded down. So we need to buffer all 16 of these outputs as well. So it's time to make a design, cut them on the mill, and plug them in. All right, and here's where we left off last time. From left to right, we've got our skip control up here, and then we have 4 D flip-flops, and then we have essentially 8 cathode follower buffers for the output and inverted output of each D flip-flop. And then we have a decoder that takes the 4 bits from those flip-flops and breaks it out into 16 individual signals. As a matter of fact, the only thing that's changed is I had to put it on this separate board here because it was starting to get too big to move around. So what we need to add this time is individual cathode follower buffers for all of the 16 steps that are coming out here. So I've got a whole lot of circuit boards cut up for that, so let's go ahead and plug those in. So that's a little ridiculous. It's starting to get way too long. So this is actually as wide as I'm going to let it get. It's time to start building down from here. And so on the very ends, both this board on the far left and this collection of boards on the far right, these are kind of our termination boards. They carry all the signals that are going to go to the boards that are going to be below this, as well as large power buses that run top to bottom on both sides, the left and the right. And the traces for these power buses are actually 2mm traces. And then each one of these rows of tubes has its own power bus that kind of runs along the top of it there. So we've essentially got 2 large power buses on the far ends, and then 4 smaller power buses that run down the center. So I'm hoping that that'll keep power distribution appropriate. Now, speaking of power, the power connection pins are on both of these boards here. So I need to find a way to plug those into my power supplies. So I actually made up a little harness. Let's go ahead and plug that harness in. All right, and then the other end of this harness just has some banana plugs that plug straight into my power supply. All right, well, that's all well and good. We can now put power into it, but we also need to test it as well. So I'm going to hook up a little breadboard with some toggle switches on it so we can test it out. Okay, because the harness is taking up pretty much all of my extra pins for power and ground, I have to use these little alligator clips to get power and ground over to the breadboard here. It's a little precarious, and it seems like there's the possibility for shorts very easily, so we may get some sparks. I hope we don't. All right, and then to measure the output, instead of using a bunch of LEDs hooked into our pins down here, I'm actually just going to use my little digital multimeter here. So that way I can actually see what the output values of these pins are at. All right, I think that's everything hooked up. Let's kick the power on and see what happens. All right, we had a massive inrush current spike. That is a problem that I have been ignoring for as long as I can, and I'm afraid I'm rapidly approaching the point at which I can no longer ignore it. But as we're all warming up here, I can see that we have initialized into 1000 here, and it seems to initialize into that state every time I power it on. I would have thought it would have been a little more chaotic, but I guess the tubes are warming up in a predictable pattern. So every time I power this up, we end up on instruction 1000. So let's go ahead and reset this to 000 over here. Okay, there we go. So all 4 of our VFDs are off. And let's check the far right pin here. That's going to be the pin that corresponds to the address 000. So we should see a logic high on this. Yeah, there we go. Check that out. 22.6 volts. Now, all the other pins should be logic low. So there's pin 2 at 3.3 volts, 3.5 volts. Okay, so it seems like it's working like it should. We have a logic high on the far right pin over here, and then the rest of the pins are logic low. Now, our logic lows aren't quite as low as I would have hoped, but anything under 5 volts is still a win in my book. All right, so let's check another address. Let's go to 1111. So I'll toggle the clock. Yeah, I can see all 4 VFDs came on. So now we have a 1111 stored in here, which means that our far right pin should now be logic low and our far left pin should now be logic high. So here's the far right pin. Yeah, 3.6, that's a logic low. And then we go to the far left pin here, 23 volts, logic high. Yes, that is working. We'll test one more address here. We'll do 1010. So we have 1010 stored in here now. That should be about the 10th pin. So there we go. I totally guessed and hit it. All right, so but yeah, check it out. 21.8 volts on that pin, and everything else is at logic low. Yes, awesome. So that's working exactly like we wanted it to work. How cool is that? This thing is so epically cool. I mean, it's hugely wide. So I just want to give you guys an idea of how big it is. I got a ruler here. All right, so we'll set that right there, and it is 670 millimeters wide. But, you know, that's about as wide as I'm willing to push it. So it's time to start building down. And And as we saw earlier, building down, we're going to run into our newfangled arithmetic logic unit. There's going to be a lot of interesting changes there. So I'm going to hop back on the computer and start working on the design that's going to go beneath this, because we're building down now. And this is, I just cannot believe how cool this is. We have a colossal number of tubes and everything is working exactly as I had hoped. I'm so happy about this. So thank you guys so much for watching, and we'll see you in the next episode.